All right. Welcome, everyone, to this joint MICDE-Aero seminar. Very excited to welcome Janssen to Michigan. I think it's your first time here?
First time, yes.
Very cold welcome to Ann Arbor. He has done a number of amazing things. He is currently the group leader for materials informatics at the Max-Planck-Institute for Sustainable Materials, previously called the Max-Planck-Institute for Iron and Steel Making, which is why his package is called pyiron, right? So he has to now make it pi-susmat to make it sustainable. And before that, he was at Los Alamos as the director's postdoctoral fellow, a very prestigious fellowship. And he was part of the Exascale project, which actually we had someone covered the Exascale project. He's managed it. A person who ran it, yeah. He's part of many different open source software development work. I think one of the things that I think is really exciting is as part of an LLM for chemistry, initially a hackathon, they built a very, very cool workflow with which you can run sort of sophisticated atomistic simulations, so very highly capable simulations. We were inspired by that work, and he was kind enough to support our SciFM summer school, where he co-led one of the thrusts. I think Ziki, sitting here in the first row, worked with him closely, and they actually just we've submitted a first workshop paper on this topic. And I think it's a really exciting frontier where Jan's, I think, one of the pioneers. And so I'm very much looking forward to the sort of possibilities with respect to agents and how that can accelerate materials discovery. So without further ado, right, over to you.
Thank you so much. Jan, thank you very much for coming. I try to keep this very open, so if you have a question, just ask me or raise your hand to really have like a discussion and make this. I guess my goal is to show you a bit what is currently possible with the large language models and how much is still missing for the large language model to predict a new material, right? So what's going to be the first material predicted from a large language model? And that's maybe a bit of the goal. Right? So that's where I started ambitious and said, okay, how can we predict the materials of the future and then really accelerate this discovery? And the way that we do this at our institute is really we try to use atomistic simulations to iterate over the whole periodic table and then find the alloying compositions which we can use for these future materials. And this is something that we do for quite some time already with the pyiron framework, but as Venkat nicely pointed out, we started this year to couple it to large language models to then see, okay, can we train the large language model to run simulation? And what is missing for a large language model to then do independent research, right? So I feel this is a very exciting time because it really helps me to rethink again, okay, what do I do as a scientist, right? So what are the steps? How do I come up with my ideas? And some of them, right, so I'd like to take long walks and then comes an idea, but to make this systematic and think about, okay, how did we come to this idea? What were the steps that we need to go? And how can we teach somebody, either a student, or how can we teach a large language model to come up with similar ideas? And so that's going to be a bit the structure for the talk. So I will start with one example, just how we design materials, just to get everybody on the same place, and then jump into the large language model, show a bit what is possible today, and maybe also where we have challenges, and then see how we can address those, for example, with simulation workflows and what is required, what kind of simulation workflows. Good. So as I said, maybe I can hide this. Good. I have a bit more. Yeah, so we really want to be able to iterate over the whole periodic table and find new element compositions. And sorry, no, I can't. One element that we really looked at quite a lot was magnesium. Magnesium is lightweight, so we would like to use it in a wide range of different engineering applications. But as you see here, already at 10% compression, it becomes brittle. And so we can't use it for most of the applications. And that can be explained, and I just keep the material science part here brief. It can be explained because the dislocation slip systems, there are only two slip systems available, the basal one and the tensor twin one. So the dislocations pile up and lead to fracture inside magnesium. It was already well known before our work that if we enter rare earth elements, like yttrium, for example, we enable the pyramidal slip system, and with the third slip system, then the dislocations can propagate more freely through this material, and we can compress the resulting alloy up to 50%. Now, yttrium is a material that we don't like to have if we want to be sustainable, and so we were now looking for ways how we can replace yttrium and what elements can we consider. And so that's where we started and iterated over the whole periodic table and said, okay, maybe we don't find a single element, maybe we find a ternary alloy that can be used to replace yttrium. And so we defined here this yttrium similarity index. We have the first element on the x-axis, the secondary element on the y-axis, and you can see a bit how the properties change in this yttrium similarity index. What we can do as a next step is say we apply a filter, and we only consider alloy compositions which are 95% similar to the results that we have for yttrium. And we see this, these are the bright spots in the upper half here. And for example, you see the lanthanides, they have similar properties, but they are maybe not the ones that what you want to use in your sustainable materials. And so we do a second filter for suitability and the cost, and then we find that aluminium calcium is an alloy which is very ductile. And this is really the important part about the story. We first predicted this from ab initio, from our atomistic calculations, took the concentration that we got as a result, went to our experimental colleagues, they realized it, and they found it can be really compressed up to 50%. Right? So that was really the amazing part. And for me, what really fascinates me about material science is if we look here at the concentrations, right? So we have 1 weight percent of aluminium and a tensor weight percent of calcium. So it's roughly 1% of our material that we change, and we can compress it up to 50%, right? So drastically different material properties by just doing this kind of very small change. And these are the kind of element compositions that we're aiming to find and where we do these kind of studies. And obviously where now the motivation comes, can a large language model also do a similar study and find these kind of compositions? And so with this index, we started from ab initio simulations and afterwards validated experimentally. And now if we look at the literature, there are currently a number of publications covering and promising that it's now possible that a large language model can find this, right? So augmenting large language models is chemistry tools, the AI scientist who has fully automated open-ended scientific discovery, atom agents, alloy design, discoveries through physics-aware, multimodal, multi-agent artificial intelligence. You can trust me, if one of these things would work, we wouldn't be sitting here, right? So there would be so many new material. There would be no more need for us. So we can be sure maybe they're in the publications, but maybe there are still certain limitations. And so I want to use the remainder of this talk to, a bit for us together, look into this thing, okay, what is currently possible with large language models and where are the limits? And how can we maybe go beyond these limits? And we start very basic, right? So we go to ChatGPT and we ask the question, calculate the bulk modulus for aluminium using ASE and the EMT simulation code. So what do I want? I want bulk modulus for aluminium, and I'm already giving a lot more information. So I say, please use the ASE framework. So that's for atomistic simulation environment. That's a very popular software in our community. And EMT is one of the standard methods in their framework, which doesn't require any additional parameters to be set up. And then ChatGPT gives me some explanation starting from the installation. I skip this part here, and I really just look at the simulation code that it produces. And I copied this code to run it in a Jupyter Notebook just for us to see it and for me to validate, okay, what is really happening there. And we see, okay, it's using the ASE package. That's very good. It figures out, okay, it's doing the structure calculation for aluminium, so we're also happy there. It provides additional parameters which wouldn't be necessary, but which are also not wrong, so that's fine. It's choosing the right mode of calculation. And then I haven't said anything about what level of strains it should apply, so it makes an educated guess and says plus minus 6%. I think that that's a reasonable guess. It runs these calculations, it executes a fit, everything looks great, until we look at the bulk modulus, and 0.26 that's bad, right? So this is not only wrong, this something went completely wrong here, right? So that's experimental value is 62. So now, who can spot the mistake? Who's familiar with ASE and knows where it went wrong?
Nobody's going to admit they are familiar with ASE.
Okay. Then I show you. If we look into the fit function, there's this ugly part that they have different units, right? So the units is something that we as physicists were trained in converting units back and forth. So because it's electron volt and angstroms, and we not need to go to gigapascals, we need a unit conversion. It is there in the source code. Unfortunately, the large language model didn't see it. But this is if this would be a student, I would say, 90% right. Maybe I just subtract 1 point out of the possible points. If it's a scientist, it makes no sense, the result. Right? It's like achieving, and if we claim, okay, large language models can now do 90% or something, that's nice, but it doesn't help us to do science. Right? So that's, I think, the important part. Here I show what is the solution, what I would give as like when I would run this simulation, and what you see, there's one function that calculates equation of state function that already covers all the functionality that the large language model now reinvented. Right? So we also want to see some way, can we teach large language model? Okay, when you calculate the equation of state, then please use this function. Here, by the way, you see also the value, right? So I did the unit conversion. We come to 40. There's still a discrepancy to the experimental value. This is by choosing this very simple model. There are more advanced models that I will show later where we get much closer to the experimental value. But just to say 40 is something where I say, okay, yeah, that makes sense. 0.2, that makes no sense, right? So just to get a feeling for these values. But the challenge was really, can we now tell the large language model, please look into the library and see what functions are available, and then apply those functions for your calculations, rather than starting from scratch and writing your own idea how you would calculate this quantity, maybe based on what you find in the literature. It's a 90% correct, but the scientific result is still wrong. And then we learned about this kind of idea of coupling Python functions to the large language models can be done with simulation agents. And that's what I show here. We use here the LangChain package. And the highlighted part is really just what we have to change. And even for those who don't know a lot of Python, the first part is a decorator. That basically means I apply one function on top of another function. It's just to show basically the large language model, this is one function you have access to. Right? So when I put the decorator on there, it's registering the function, and the large language model can use this function. The next step, I define the function call. I say, okay, you get the chemical symbol, and then I provide what's called the doc string, so some level of documentation. This function should return the structure, the crystal structure for this. And we see, okay, what I do internally, I use the ASE database, and I just, from ASE, ask the chemical symbol, and then get the reference crystal structure, and if there's no crystal structure, I give an error message. One way to think about this, or a reference that I like, is to say, think about the header files that we have in C++ or in C, right? It's like, which functions are publicly accessible? Those are the functions that are now registered to my large language model, so they can be used from the large language model, right? So with these decorators, we just put the decorator on, and these are the functions that we want to have publicly available, and other functions are maybe just internal in my Python library. All right, and this is now a demonstration. You can also look at this on your own on the website, but just how this simulation framework could then be used. Right? So here we have a chat conversation in our Jupyter notebook. I ask for the bulk moduli of the noble metals. It executes the calculation. It gives me some values. Then I can ask an additional question, maybe give me a comparison to experimental values. So it's really at this level where I can talk to the machine and get an answer and do some kind of, at least on a small scale, some discovery, what are the properties for a given element. And what's happening in the background is that, as you see this here, is now really invoking these Python functions that we defined before. In the background, I defined a couple more, right? So we first get our crystal structure. We get it now as an ASE object. Right? So we take our chemical symbol. It's able to figure out, okay, when I iterate over the noble metals, I want to have gold, silver, platinum in there. And then it knows that the chemical symbol of these metals and how to translate this, right? So to have the input for this, and then it has the first structure, and then for this, it takes the structure, so the output of one function as an input for the second function. So it's able to not only call individual functions, but also then couple these functions together and really build more complex workflows in this way. And so it's really able to use these specialized agents to then address the first challenges. And we can go one step further, and because up to this point, the large language model was just like a user interface. I can write the Python code, or I can use the large language model, but it's not really adding any abstraction or any thought process on its own. And so now in the second example, I want to show how we do inverse materials design based on the large language model by me defining a function which goes from elements and concentration to a material property, and I again take the bulk modulus, and then I ask the large language model to invert this function and say, give me the concentration where I measure a specific bulk modulus. Right, so now it has to be a few more steps. It has to do an iteration, maybe run a loop, do a linear interpolation, as we see here, to see, okay, where does it match? And then say, okay, where do I get these properties? And then also this works fine, right? So then it's able to figure out, okay, we get roughly 70% or 74% copper, and the rest gold. That's an alloy composition where this is in there. Sure, you can also do this with Bayesian optimization or other tools, but just to show at this stage, I only have to define the Python function, and in my case, it's now a Python function for a specific simulation, but you can have any other Python function, and you say, okay, now I want to invert this function, and the large language model can take care of this in a first level of abstraction, right? So it's already nice. But it's not all nice with large language models, and so maybe now I come more to this big topic of hallucination and the limitations of our large language models. And there was a nice paper from people working at Apple, and they have fruit examples, surprisingly, where they just added additional information and saw how can we distract the large language models. And so the information that a few of these kiwis are a little smaller than average doesn't really change the result how many kiwis are there to calculate. But the large language models get very confused by this statement and subtract the 5 ones. And this is now an example here for this. We come to the same issues also for our own questions. For example, what is the crystal structure of a car? That makes no sense, right? So we could say, okay, maybe it finds the best alloy, right? So maybe it tries different things, but it goes completely wrong. It says, car, that starts with C, so it's carbon, it's diamond structure. So that's really the dangerous part, right? So these large language models, unless we restrict them in a certain way, they can go completely wrong, and they're absolutely convinced that they're on the right track. Right? So there's no checking, does it make sense? We have to be careful that we implement these checks or validate these results. So also for my students, I say, please use the large language models, play with them, but you're still the one who's responsible for what comes out, right? So don't come to me and say the large language model told me so. No. Right? So we have to be very careful when we use these tools, because there's no reflection on this, and that's really the dangerous part and where these hallucinations really come into play. I think in contrast to traditional programming, also we lose this deterministic way. It can be that it's 90% it's producing the right result, and then 1 out of 10 it just gives a totally different answer, and we have no way to be really sure, in particular when we build more and more complex of these workflows. And there are a number more parts, right? It's like we struggle when we have a single function, maybe 2, 3, 5. That still works fine. If the number of functions grows larger and larger, suddenly the large language model gets confused and is no longer sure which function should I use for which task. We can then think about, okay, we build a hierarchy of different agents and say, okay, everybody only has like a small number of functions. Then they have to coordinate with each other. But there's really seems to be like somewhat like a mental capacity of the large language model, which is currently still rather limited, that as soon as it has like more than 10, roughly more than 10 functions, it should choose from, then it gets off-tracked and really has issues there. And then also this question of, okay, what kind of mathematical capabilities has large language model? It can do linear interpolation, but when we now go beyond linear interpolation, maybe we want some quadratic models, maybe other models, where are the limits? And also what, in particular because it's commercial models and we can't really look inside them what's really happening, do they have agents on the other side, right? So like if I ask them to do linear interpolation, do they know, that's something where our model is not so good and they just call an agent and evaluate it? It's hard to know, okay, what's happening there. How can we improve the performance? Solution is usually to prompt engineer, to provide more details and then more restrictions of the flexibility. And how can we orchestrate this? And I think all these topics are really where it's required to have some more benchmarks and where we as scientists can develop kind of prototypical cases where we test our own abilities and then see how does the large language model perform on those. So that's the first overview of using the large language models. Before I now come to the next part, I just want to see if there are any questions at the moment, if somebody wants to ask something.
I'll
Sure.
tee one up. The search problem, right? So the inverse design problem. So what is your thought process on the prospect of these large language models being better than Bayesian optimization? In the sense that a Bayesian optimization, right? You're feeding in a certain variable, but you don't feed in all these sort of hidden priors that a large language model might have about, you have copper and gold, right? Maybe you know that they mix linearly or they may not mix linearly, right? And so a large language model might be able to do that search more efficiently. And I think there's a bunch of folks that have proposed that they can be used as optimizers.
Exactly. So people propose this. I think the question is still like how much hallucination is there, and how can we know that it has like a physical reason why it makes these decisions, right? So I think the fear is a bit that today it makes one decision, tomorrow it makes another one, and it never really explains us, or at least most of the models don't really give an outline, okay, this is why I made this decision, this is where I got the reference data, right? So I think we need some, like we would ask a student, right? So we don't say pick A or B, but why do you pick A, why do you pick B? And then there I'm still not sure how we can either have this documented, to have like we have logs where it says, okay, I now choose this option based on these parts or something in this direction.
So if I'm with Sanjeev Arora's work on decomposing the data into tasks and skills, and he tries to compose different skills, and he sees that the largest model was able to do composition of 5 things.
Okay.
Slightly smaller collapses at 3. So he had a very specific way in which things collapse. So it's basically failure of composition. And he was not doing science, he was just doing language. So
I'm not aware, but I'm very interested in this work.
We can chat more. We talked about it quite a bit as well. And we can talk more. But related things, I think.
Because I'm looking now for benchmarks for these kind of agent-based models, and unfortunately most of them are like crawl this website or we're not so much on our application of saying, okay, I want to call a Python function and I want to build the complexity there. So I'm very interested if there are already benchmarks.
Benchmarks for language, particularly for compositionality. How many things can you put on top of each other before it falls apart?
Okay. Any questions from the students? Okay, it only gets harder from here, right? So that was the easy part. Good. Now we want to look into this question of like calculating the bulk modules and consider the ab-initio precision. And I want to use this a bit as an example of us to think about what is like a good function, and is a function that's easy to use for us humans also a function that is easy to use for the large language model, right? So really, rather than using the large language model as like already on the stage of, okay, can now design its own materials, can we maybe use the large language model as a tool to validate our own workflows and say, if the large language model can use my workflow, then the chances are high that also humans can use it. If the large language model struggles, maybe it's also hard for other humans to work with the workflow. There's an easy one. And I brought 3 examples how a Python function could look like. And maybe just to wake up the students a bit more, which one would you prefer? Right? It's like, do you want to have like input files, maybe in a very specific format for a specific code, or maybe a generic format where it would be similar for all codes, but like still technical parameters of like, for the specific method, in this case, plane wave density function theory, or when we calculate the bulk modules, just ask for the precision of the final result that we want as an output.
Definitely C. I would go for scientific interface.
Yes. And why?
Because that's what my PI would ask me to do.
Then you have very good PI. Right, so it's the same thought process, right? It's like to find the ones where we give these values and to think about, okay, what would my PI ask me to do? Maybe that's how I should design these functions, rather than what we commonly still find a lot in scientific software of like, okay, here's this input file and this input file, I run the calculation, and what is in the input files and how they were generated is happening in some other function.
How do we know the precision? If you don't know the reference, how do we define the precision?
That's what I will show on the next slide. Give me a bit more time. So that's exactly the important topic, right? So it's not so easy. So this step is easy. I can still write the input files inside my function, and I can also say for all simulation codes, I agree on somewhat of a generic format. I always use the same units for my inputs and the same units and variable names for my output. But I completely agree the step from this generic interface to the scientific interface, that's really where things get challenging and where we have to rethink the algorithms and what we use there. Good. A brief reminder about density function theory and the precision in there. We just, I guess I have it here, right? So like we have our G vector and then the K vector. And basically whenever you increase our energy cutoff, or if we increase our energy cutoff, that equals extending the radius, how many plane waves we consider, right? So we include more plane waves to describe our electronic structure. And if we increase our K-point spacing, this means increasing the number of gray dots. And so you can see directly there's a coupling. When I increase my cutoff, I have more gray dots within my radius. And in the same way, when I increase my K-point spacing, I also have a coupling there. So on the high level, it's just you can't converge independently on the energy cutoff and the K-point mesh, but these two quantities are always coupled, which can be shown by this very basic equation, which you find in every PhD thesis discussing DFT or plane wave simulation, plane wave basis sets for DFT is covering this. And we again come to our bulk modules, right? And we can think about, okay, how do we now define our precision? So here I plot the bulk modules of our energy cutoff. And we can then say, okay, what is our accuracy? And accuracy is still in reference to experiment. So there might be limitations in the choice of pseudopotential or how we construct our DFT calculation there. But what I primarily now care about is this level of precision, because that's something we can reasonably or relatively easy control. By modifying my energy cutoff, I can reach different level of precision. So now to design this kind of algorithm where I just say, okay, what is the precision that I want to have access to this parameter, and then also not only over the energy cutoff, but also over the K-point mesh. And so the accuracy is given by the measurement to the true value. For us, true value in this case is experiment, and then precision is given for the finite basis set when we restrict our part there. And here I now show for the energy cutoff and the K-point mesh on the axis how the value of the bulk modules changes. And I pick the top spot, so the maximum K-point mesh, and the maximum energy cutoff as my reference. Right, so there exactly we have this reference that we compare to, and then you see how this is varying over these different calculations. And here, this case, I really did all the calculations, and like 50,000 calculations, which is definitely not what you want to do for every time when you evaluate this, for every kind of convergence test. But what I will show in the following slides is you can get to the same result, and it's nearly the same, right? So there are small features where we see that it's not exactly the same, but very close, with less than 10% of the calculations. Right? So to make this transition, to go from a generic input to more scientific input, where we can predict the whole convergence behavior over the whole parameter range, and then from there make a statement, okay, how much is still missing until you reach this precision, we need to develop new methods how we do our convergence tests. Right, so systematic convergence 10 times less. I keep this brief. We can think about this as this kind of cube. Right? So on the one axis, we have k-point mesh, energy cutoff, and then these are all energy volume curves. So the third axis is how the volume changes. And now I only take the extreme curves. Right? So like at the minimum k-point mesh, minimum energy cutoff, and then I look at how it changes over the volume. Right? So that's minimum, that's the orange curve that we have here. Minimum k-point mesh, minimum energy cutoff, how our energy volume curve looks like. And then I can take the other one, right? So maximum k-point mesh, maximum energy cutoff, that's the one up here. And then the ones in the middle, right? So minimum k-point mesh, maximum energy cutoff, this is here. And then the red one, maximum energy cutoff, maximum k-point mesh, and then the energy cutoff. We have these 4 energy volume curves. And so now we can look at the differences. We calculate this difference, for example, we choose the 2 curves with a maximum k-point mesh. Right, so this one and this one, and they just subtract them from each other. No, this is here. We keep one parameter fixed, right? So let's say we keep the energy cutoff fixed and subtract the minimum k-point mesh and the maximum k-point mesh. One's at minimum energy cutoff and one's at maximum energy cutoff. Right, so this is one pair, and we see no matter the difference between the 2 k-point meshes is more or less independent from the energy cutoff that I use. And in the same way for the second part, when I keep the energy cutoff, the k-point mesh fixed, the difference between the 2 energy cutoffs is also more or less independent. And then as I have these 4, I can also take the remaining difference then of them, and this is just a statistical contribution. And so by separating this uncertainty in like 2 systematic contributions and 1 statistical contribution, I break down the problem and I can describe it much more easily for me. Right, so that's what we do here. I also try to illustrate this a bit graphically. And so the 2 systematic ones, and then the statistical one where we just use the opposing sides. So we have our value at the maximum convergence parameters. Then we have a systematic correction for the energy cutoff, a systematic correction for the k-point mesh, and then a statistical correction for the last part, which I showed here. And with this approximation, we are then able to predict the uncertainty over the whole parameter range. So basically, if we think about our cube, by only looking at the outer surface, we can predict all the points inside the volume for this particular challenge, because we can decouple the energy cutoff in k-point mesh. The other part that this allows us is to look at the systematic contribution and the statistical contribution separate from each other. Right, so I show this here for aluminium. For aluminium is an easy case because we basically see that the statistical error at no time becomes dominant. Right, so it's always a systematic contribution, so you can completely neglect the statistical contribution. But if you look at other elements, let's say copper, we see these are much more on the same level. Right, so there the statistical error is much larger in comparison to the systematic one, and they really meet at some point. And that's what we then showed here in what we call the error phase boundary, where both errors are on the same level. That's where we define our boundary. Right? So like in this top part, the systematic contributions are dominant, and then in the lower part, the statistical contributions are dominant. And if we look at these parameter ranges, right, so like because we chose a very extreme parameter range for this study, right? So rarely people use a energy cutoff over 1000 eV, and at least VASP at the time still needed modifications on the code to be even able to go so far. This is usually the range where most of the studies are done. Right? So while there are elements where this systematic error is dominant, like aluminium, there are others where for most parameter ranges that we look at, the statistical one is dominant. And we rarely reach the systematic one, only if we go to very high convergence parameters. Right, so the important part, statistic, is a multiplicative convergence, and then systematic is additive convergence. So we also have different strategies how we address the error once we are in one of the different regions. And then we can use this technique to really sample the whole periodic table, because we save this order of magnitude in calculations, and look at how does the convergence behavior change for different elements. And for example, if we now go again from copper, silver, gold, we see how the dark green area, maybe here is an example, how it's extended down there, and how then the area here is moving over. Or if we go from gold, platinum, yttrium, also there the K-point mesh is the dominant factor, depending on where you navigate on the periodic table. Good. So there was a second part, a bit about the details of DFT simulation. Are there questions about this part? And I hope what I really wanted to highlight here is that to make our workflows more accessible to large language models, but also for us as expert users, we need to rethink the way how we look at something like a convergence test. But once we did this and implement this, for example, in a Python function, then it becomes much more usable also for the large language model. Sure.
There are a lot of, when you DFT calculate like a shear modules for transition metal, there is already a very large error between DFT result and experiment. So can this large language model somehow correct the term? Okay.
So there are two things, right? So like, if I get the right value for the wrong reason, is it something that I want? So that I don't want the cancellation of the errors. I want to be able to predict how these errors propagate through the different materials. That's one part. The other part is because the pseudopotential that you use underneath that we are effectively sampling with this technique are the same. We hope that there's a correlation for the convergence of the different errors. But so that the error of the bulk modules, for example, converts somewhat similar to the error in the shear modulus. But that's currently a hope. That's nothing we have validated yet. We are at the moment looking at phonon calculation and see how much this methodology can be transferred to phonon calculation, which are more dependent on the forces of the atoms. But that's the two directions. So.
Thank you. Yeah, that's a very interesting direction, because if each property has its own error phase boundary, right?
That would be bad.
Then we're in trouble, right?
Yes.
Which is actually what we do anyway, right? Like we almost never calculate the error.
We would hope that people do it.
We usually just do the energy and check the energy convergence to sort of some level, and then just call it a day, right? So this is really intriguing.
Yes, I think like we picked the bulk modules here as an example because we have the volume dependence, and we see that that has an effect. So I think just the energy is dangerous because at different volumes, or if you have different cells, strained cells, cells with defect, cells without defect, then I would still do the convergence, but still we hope that there's some general understanding that we can discover with this kind of method, and then be able to automate this process.
Do you have a field? I think LangSim's question of like shear modulus, like, do you think the error phase boundary is very different? I mean,
I don't make a statement on recording. Obviously let's say for these structures that are by deforming the supercell, we would assume that there is some relation. Structures where like the phonons, where we just move single atoms, we don't think that there's such a strong correlation. But I can't make an approximation at the moment how this how this would look like.
And I guess these boundaries will change if you change different exchange correlation potential.
Yes, yes.
And this was done with PBE, maybe?
Yes. So for our calculations, we primarily use PBE. So unless stated otherwise, all these calculations are with PBE. But yeah, that's definitely also a question. And then even for PBE, there's a question how many electrons you include, which could affect this result as well. Many open questions, many.
Another thing you mentioned is the pseudopotentials themselves. Buzz
Yes.
does not allow to do any changes in pseudopotentials, for example.
Yeah.
Another.
But I think, so the hope is that for every pseudopotential, you would once calculate these maybe two basic properties. Maybe let's say we have the bulk modulus and then phonons as like a property which primarily depend on the forces. And then based on these conversions, you would make estimates on the larger scale. That's the goal. Good. Yeah. So now I switch a bit and then go really to the stage of how we currently do our workflows and explain a bit the tools that we have, which then give us hopefully also an opportunity to see how we can connect them to the large language models in a later stage. As we now have 20 minutes left, do we want to have a discussion at the end or?
No, 20 is okay. Yeah.
20 is okay, then I go for 2, good. So this is our pyiron framework that was a major part of my PhD thesis. And what we used before was really on the command line, a very standard, similar to like my professor started before, right? It's like on the command line, changing files, moving files around. And what we tried here is really to be inspired from the data-driven approach or the tools that are developed in the data science community, in particular the Jupyter notebooks. They allow us to take a look at our structures before running the simulation. There were a large number of calculations before where people just built the structure, had overlapping atoms, submitted it, it crashed directly, but it was a waste of time, right? It's like sometimes it helps to look at the structure even if you believe you did everything correctly and set everything up. The other part that I find is very nice is this option to have like markdown text inside your Jupyter notebooks to write down a bit, what do you want to do? What is your hypothesis? What do you expect to get as a result? Again, to document a bit what was our thought process when we run these calculations. At the same time, if you do it in a Jupyter notebook and you document this, and after you comes the next student who wants to use the same method, it's very helpful to have some documentation in the Jupyter notebook and see a bit how it can be used and what is there. And then we cover the whole process from setting up the calculation, running our results, and even the analysis, ideally all inside one Jupyter notebook. And so the goal where we want to go with this is that if you get a figure in the publication and somebody asks you, how did you create this figure? What calculations went into creating this figure? That you're able to say, yes, this is a Jupyter notebook. In the beginning, I set up my calculation. In the end, the figure comes out. If you want to reproduce it, run the same notebook. Right? Because at least for us, previously that was very challenging. If after 3 months, after 6 months, maybe after a year, somebody comes and says, okay, how did you get this figure in your paper? Then there was some data that was run on the cluster, then the values were copied over, maybe in an Excel sheet, maybe there was some manipulation, then the data was saved in a text file so that it can be plotted with gnuplot. And there was no chance to reproduce exactly how it was done. The general understanding was there, but like it could again take a week or 2 weeks to be able to fully reproduce it from the raw data. And with this, what we address with the Jupyter notebooks. And then we aim to make it also very intuitive or in particular interactive, right? So like what you see here a lot is that we define this project object. You can think about the project just like a folder on your file system. But then from this project object, we create the next object. So in this case, a LAMS calculation, so it's an interatomic potential simulation code. And then by creating the project, the LAMS job from this project, it already knows that the data of this LAMS job is saved in the folder of this project. So we implicitly communicate this hierarchy just by the way how we construct the syntax. Or in the same way for our structure. Another part that really helped us to accelerate the way how we develop our scientific protocols is connecting to databases. So the NIST, the Institute for Standard and Technology, provides a large database for interatomic potentials. When you call this job.list potential function, we have a cached version of this database, and we list all the potentials that are available for your specific structure. So in this case, all the potentials which include kappa as an element. So rather than you going to the website, looking at the data, selecting a potential, downloading it, copy it in the folder of your calculation, all this is done automatically in the background from the software. Because we say, okay, this is a step that comes over and over again, so we just implement it, we just automate this part. Right? And that's what you see here. Finally, you can very easily select the number of cores and how you want to submit your calculation. So also the process of like talking to your queuing system, maybe copying files to the computing cluster and all this, we're already hidden behind this framework. And that's now obviously a large advantage, right? It's like when other people struggle to allow their large language models to talk to a supercomputer, we say, we just write our own code. We already solved this problem for the humans. The large language model can connect to the same framework, write the same Python code, and run the same kind of simulation. In the background, this is realized with like an object-oriented approach. So we have our connection to data storage, that we use the HDF5 format, particularly to store long trajectories in a very efficient way. We have an SQL database, primarily as an index of all the calculations that we executed. We have resources like information about our computer cluster, specialized simulation codes like the VASP code, what we saw before, and parameter databases like the interatomic potentials from the NIST part, and then the user interface, what I already showed in the Jupyter Notebook. Right? And by having these kind of pyiron objects representing all the different codes, we can replace one code with another one. So a typical example is that we first run the initial tests of like supercell size conversion, other factors with an interatomic potential, and only once we understand the problem there, then we turn on the DFT part and run it on a larger scale. So we abstract the technical complexity to really focus on the scientific implementation. That was really one of the core goals to develop the pyiron framework. And with this, and that's maybe the most recent extension to this, we now try to cover the whole workflow of generating machine learning potentials. And so we start in the top left by building a very diverse set of structures. The goal there is that we don't want to have any kind of bias in our structures when we generate the spaces, but really cover a wide range and then be able to evaluate them with DFT. We then support different kind of machine learning potentials just to see is there any specific reason why one potential should be better than another one. In this collaboration, we use the atomic Rex code for embedded atom method, the runner potentials from Jörg Behler as neural network potentials, and then the atomic cluster expansion from Ralph Dodds. Still, we primarily these days use the atomic cluster expansion for most of our systems, but having access to the other ones is again one of these advantages of having a framework like pyiron where you can just replace the building block of your fitting code with one or another code, just like this. And in the next step, we do a validation. The first validation is comparing the energies and forces predicted from our potential to the ones calculated from DFT. The next step is calculating material properties like the bulk modules, phonons, or convex Hall, which are still accessible for DFT, and calculate them with our potential. And then the third step, and we can always have an active learning, right? So when we find challenges there, we repeat the calculation, add the structures, and run a next iteration. And then the final step is really calculating material properties which can't be accessed from DFT, like in our case, the phase diagram, and compare this to experiment. And that's what I show here. Right, so you see the phase diagram, right side experiment, left side is our potential. They're not yet the same. Right? So there's still work required on our side. We're still working on the thermodynamics approximations. We're now building up a database of different parts. But what we also see here, and which raises, again, a couple of questions, is there might be a dependence on the functionals that we're currently using. Right? So maybe PBE is not good enough to reproduce the experimental phase diagram. And if we're able on this level to compare to experiment and say, okay, maybe one functional is better than another one, that really helps also the other people to then say, okay, how can we develop the next generation of functionals? Right? So if we can control the uncertainty on all other levels, like what is the DFT calculations, what's the uncertainty that we have there going into our calculations, what is the uncertainty on the thermodynamic level, where we are currently still extend the models, but we're also able to quantify it there. Then we can really do a one-to-one comparison with the experiment. Good, so we can really get the phase diagram. Yeah, I guess I still have a couple of more slides, and then I skip to the end. But are there maybe questions on this part at the moment?
This is fascinating. I didn't know this. How do you think about the error from the thermodynamic integration and sort of other steps involved in going from your machine learned potential to the phase diagram?
Yes. So basically, each of these points, we can think about it like an MD trajectory at the specific temperature and specific concentration. And then we can, one way to do is thermodynamic integration over different methods. Right? So we can couple our lambda parameter between DFT and the machine learned potential. What we see in particular with the machine learning, so that's what we did previously, and that's still computationally very expensive because we have to once run the DFT thermodynamic integration. We find there's even with a traditional ERM potential, there's only a few steps required because the curves are already very similar. And so the big difference is going from the reference system, like our harmonic system, to the potential. That's where we need a lot of sampling points and where we have the complex sampling. Going from our potential then to DFT is a much smaller part. And for these machine learned potential, it's usually even enough to just do a perturbative approach. Right? So we just, from our trajectory, we pick a subset of configurations and check how much is the difference. And if it's below our precision level that we aim for, then we're fine. But you can really have ab-initio precision on all of these points.
And this is fully automated? Like you can produce a phase diagram?
There's a reason why we go to 0.5 and not beyond, right? So like lithium is a very tricky system, and we are working on making this automated, but that still takes a bit more iterations. So yeah, the goal is to get to it automated. To say today it's fully automated is an overstatement.
This is really cool. So, but when you fit in potential, it's based on my experiments, it's very difficult. On one hand, it can duplicate thermodynamic property like phase diagram. On the other hand, it can show good type defect property away from ground state, like a migration barrier, deswing co-energy, someone. Could you comment right now, so far, for example, right now the fit potential for aluminum decent can duplicate phase diagram, but it can also show some defect property, like a migration barrier. Or
I come back to your slide. A question on the next slide.
Wow.
Maybe one.
He already knows what is your next slide.
I guess I was.
You said coming from the reference, your harmonic system to your potential part, you said you need a lot of sampling, but then with the machine learned interatomic potential, it is quite costly to run all those simulation. So it's even feasible to run all those sampling with machine learning interatomic potential.
I guess costly always depends on your reference, right? So DFT is much more expensive, and the machine learning potential is still very cheap compared to DFT. Yeah. So I think the cost of the machine learning potential is something that we are willing to invest. The cost of DFT, we don't want to run the MD, like if you would go directly from DFT, from the harmonic reference to DFT, that would be too expensive. Having this intermediate step of the machine learning potential is much cheaper.
Is there an estimate on, say, how much time it takes to generate one point?
The overall part here at the moment, what was it? I guess it's 100,000 CPU hours for one phase diagram is a rough number. So it's not cheap, but it's also not expensive if you look at the current CPU clusters, and then if you go for GPUs, right? It's reasonable.
Yeah, 100,000 is not bad.
No, we might still, to get even more precise, but that's a rough ballpark what is required to get a phase diagram. Good, now to answer your question. what we do is we start with a very diverse set of structures. Exactly from this experience that like before we always had a bias in our structures. So what we do now is we start from the space groups. There's we generate the configuration in the space groups. We then either relax them or we disturb individual atoms from this configuration. And the advantage with this is that we have like a diverse set of small structures. So it's typically, I guess, and that's what I show here, right? So you see the per atom energy over volume, that we really cover the whole range. And we cover the whole range in this energy space, but also in terms of the descriptor space of our potentials. And so with this, we really make sure that we're primarily interpolating with our potential and not extrapolating. And as long as this is given, we trust the result of these potentials. Does it address the question? Yeah, so that's a diverse set. So I guess in the interest of time, I skip this part. And maybe very quickly go for the fitting of the potentials. The challenge here, so this was part of the exascale project. We typically, when we fit machine learned potentials, we have this very serial process, right? So we do our DFT calculations, we fit a potential, we maybe do a couple of tests with this potential, and then we find new structures to include in our training set. So if you visualize this, you really have this one step, we wait until all DFT calculations are finished, we do the next step, wait until the fitting is finished, then do the active learning. And usually between each of these steps, there's even like a human involved, maybe copying data, converting files, and so on. So now to accelerate this process and to really make it automated, what we develop is what we call the kind of like streaming workflows. So rather than waiting until all your DFT calculations are finished, we wait until the first 100 DFT calculations are finished. And then with the first 100, we fit our first version of the potential, use this first very rough potential to already do the first calculations, do the first active learning, and then when the next calculations are finished, we optimize the potential and go to the next step and to the next step. Right, so really, to always keep all resources of our supercomputer busy, right? In particular, the DFT part, which still needs the most resources, to have this always running, and then the fitting and then the resources for the active learning as well. And we applied this on the frontier system, here just with like 256 nodes, I guess. And then you see the scaling, and basically what we see there is that already within less than 2 hours, we get a first potential that matches the precision criteria that we want. Right, so it's continuous, you get your large allocation. In this allocation, it's running, doing new calculations, everywhere getting a new estimate, always doing new DFT calculations, then doing the calculation of the descriptors of this, doing one fit, and then using this fit to do the validation. And all these tasks are running in parallel until we reach the limit where we reach our convergence, and then we stop the job. But before, fitting a potential or getting a new potential was something that took a couple of days. Now it's really down to just a few hours. Get the large allocation, you run the system, and you get the result. And the next step is obviously now put the phase diagram in there as well, right? So that you ask for a large allocation, and it's using the resource until it's able, okay, this is the phase diagram that I get. My error bars are below a certain limit, and then I go to the next. Right, and this is where I come to my conclusion. I guess we're nearly close to the hour. I hope I was able to give you an overview of the benchmarking of the large language model, the capability of what's currently there, and maybe a bit the difference of what was promised in certain publication and what's actually currently possible. I gave you a short overview of the pyiron workflow framework and how we separate the technical complexity and the scientific complexity, and really how this enabled the prototyping and how it can be coupled with the large language models. And finally, the machine learning models as really one way to sample the space and have a way to identify the sustainable materials of the future. With this, I'd like to thank you for your attention.
You had that phase diagram. And so that's a very famous phase diagram. Even somebody like me knows that, right? What if it's slightly harder? And so my question is leading to, I know that, you have this huge library and you're basically guiding it. But I'm wondering what we can do from the theory of large language models to improve the behavior. Thinking more like, what kind of reasoning would you like? Anyways, there are two questions, but yeah.
Yes, so I think let me answer it also with two parts. Right? So on the one hand, we don't want to have a bias.
Yeah.
So that's why we start with very random structures and we write all this currently on as Python codes.
Yeah.
That obviously is on too much calculation. So we want to benefit from the knowledge that is in the large language model.
Yeah.
We are not yet sure how to do this. I think, or I could imagine that it could be done with some kind of uncertainty approach, where like the large language model gives us a hypothesis, this is the phase diagram we expect, and then we just validate it, and if it roughly matches what we expect, then we don't calculate the other phase of the model.